Yeah, we're live. Good. Okay. I'll try and do this. Okay. So we still have a minute before we formally start. I see about 27 viewers. Just before I make any introductions, how do I know you can see me and hear me? There's a discussion thing. Can any of you get onto the discussion and maybe send a message? Do you know how that works? Oh, two new comments. Great. They can see and hear Evelyn and Emily. Hello. Okay, perfect. Very good. Okay. Uh, I never take anything for granted anymore. So anyway, welcome to the Faculty of Science, Physical Sciences. My name is Bob Stamps. I'm the head of Astronomy and Physics Department, and this is not about astronomy and physics entirely at all. It's half chemistry and half physics and astronomy. And so what we've got are two representatives, one from each of the departments, and I'll introduce them both to you right now. There's Dr. Horace Long from Faculty of Science Chemistry, yes, and Dr. Ruth Cameron from Physics and Astronomy. So what we'll do is start with Ruth, and she has a presentation, and then this will be followed then by some time for questions, and then Horace will present, and we'll have a few more questions, and then at the end, just open for free-for-all, whoever would like to ask questions. And the questions would be through the discussion, which you've already found out. You have to, there's things which keep popping up in front of the discussion. So, but at this moment then, I'll turn over to Ruth. So, Ruth.
Hi, thanks for coming, everyone. Just give me a moment while I share my screen. And let me grab my PowerPoint presentation. There we go. So I hope everyone can see my slides. My name is Dr. Ruth Cameron. As Bob said, I'm a faculty member in the Department of Physics and Astronomy. And what I want to talk to you about today is not from my research, but actually something related to just headlines in the news from this December. And everything that I'm going to talk about today would be touched on in some aspect or another in our introductory physics courses. So if this is the type of story that interests you, maybe you should look at studying the physical sciences at the university. So I'm looking at a story which appeared in the news in December, that there was a radio signal from our sun's closest neighbor star that was a candidate to be from an alien civilization. It had characteristics that led scientists to think that there was a possibility that it was an artificial signal coming from this nearby star, Proxima Centauri. This was discovered by the Breakthrough Listen project, and so it's called Breakthrough Listen Candidate 1. And this photograph shows that nearest star, Proxima Centauri. So why was it a fascinating candidate? Well, it was a radio signal, and the first test that it met is that they only detected the signal when the telescope was pointing at Proxima Centauri. It periodically moved away, and it did not see the signal over the 30-hour period where they detected this signal. They weren't actually looking for alien civilizations at that time. They were actually studying the star Proxima Centauri, but later analysis showed this weird signal, possibly artificial in origin. Now, if it was a signal from a natural source, like something from the star or from interstellar gas, you would expect it to be a broader frequency range. This was a very, very narrow band signal, which was another thing that suggested it might be from an artificial source. We'd also like to see a signal drift down in frequency if it's from an artificial source. This is an example. Here we see a signal that's very narrow in bandwidth. You can see the bright orange indicating a strong signal is just in a very, very narrow frequency range. But as time goes by, the signal drifts down in frequency. This is an artificial radio signal from an extraterrestrial source. It is from the space probe Voyager 1. Why would you expect to see that downward drift in frequency? It's due to the Doppler effect. If the source is moving towards the observer, then the observer sees the wavefronts closer together. That corresponds to higher frequency or a blue shift. And the inverse, if the source is moving away from the observer sees the wavefronts further apart, and that's a lower frequency or a red shift. So as the Earth is rotating, a telescope is looking at the sky, and the star Proxima Centauri will first appear to rise in the east. At that point, the telescope appears to be, because of the Earth's rotation, is moving towards the source. So the signal would be blue shifted. As the source rises in the sky towards the zenith, because the Earth is rotating, the speed at which the telescope is moving towards the source slows down. And eventually, as the source passes the zenith, the telescope is relative motion moving away from the source. So you go from a blue shifted signal to a red shifted signal, or overall, during the course of an observing period, the signal should drift down in frequency. Unfortunately, the signal from BLC1 drifts up in frequency. So it doesn't totally make sense for it being a source on Earth, which is still a very likely explanation for the signal, but it's unlikely to be something just moving with the Proxima Centauri system. It could, however, be tantalizing prospect, a source that is accelerating towards the Earth from the direction of Proxima Centauri. However, based on this upward drift in frequency and further analysis of the signal and the fact that it wasn't repeated, I think it's 99.9% likely to not be from an alien civilization. Still very interesting. And why is in particular interesting? Well, Proxima Centauri, this nearest star system to ours, has planets. And in fact, one of the planets, Proxima Centauri b, is known to be very close to the star, close enough that it would be warm enough to have liquid water on its surface. And this planet is just a little bit bigger than Earth, about 25% larger than Earth. So really a very Earth-like planet, and it's in the closest system to our own. A few problems for its habitability. It's probably tidally locked to its star. And the star, the reason why it was being studied in the first place is that it has periodic X-ray flares. And those X-rays would bathe this close by planet and be not very good for the development of life on it. Still, very interesting planet. Now, how do we know that this planet is there? There is no telescope on Earth that is powerful enough to image this planet directly. So how do we know that there is this planet Proxima Centauri and its size and its orbit? Well, we detect the planet by looking at the motion of the star. So here we see a planet-star system, and they are both orbiting their common center of mass. Normally, the planet would be much, much smaller than the star, so the center of mass might even be inside the star, but still move in an orbit around that center of mass, and that would appear as a little wobble in the position of the star. If you're looking at it edge on, you could see the star moving. Suppose you're observing over here, you could see the star moving periodically towards and away from you. And remember that Doppler effect? If the star is moving towards, then the frequency of the light emitted by that star is going to be blue shifted. And if the star is moving away, the frequency of the light emitted will be red shifted. So you'll see periodic red shift and blue shift of the light from the star. And from that, you can work out the period of the star's orbit and the maximum speed that the star is moving towards and away from you. And from that, and with knowledge of Newton's laws, you can figure out what must be the size and the orbit of the planet. Now, how do we know that the frequency of the star, what the frequency the star is supposed to be before the red shift and the blue shift? Well, we look for these dark lines in the rainbow spectrum of the light emitted by the star. These dark lines are absorbed from atoms in the outer atmosphere of the star. Now we can see those, in fact, my students do look for this in looking at our sun with a spectroscope, and you see these dark lines in the rainbow of light from the sun. We can measure also the spectrum of light emitted by the atoms, hydrogen and helium usually, on the Earth, so we know exactly what frequencies they emit at. And then we can calculate the red shift and the blue shift, and from that find a planet. In fact, students in my introductory physics course right now are looking at one of these lamps. This is a hydrogen discharge lamp. It contains hydrogen gas and it has a high voltage discharge across it. That makes it glow in this characteristic pinkish red color. That color is due to these particular wavelengths of light. These are the only visible wavelengths of light emitted by hydrogen gas, hydrogen atoms. My students measure these wavelengths very precisely in the lab, and from that work out some details of the quantum mechanics of the hydrogen atom. These specific wavelengths are a fingerprint of the atom. So the signal from this very interesting planet, it probably isn't artificial in origin, but it's still really interesting, and we'd love to get a closer look at this planet. Now, at the moment, we don't have a telescope that could do that directly, but maybe we could send a space probe to visit the Proxima Centauri system and look at it. Unfortunately, even though Proxima Centauri is the closest planet to, closest system to our Earth, it still takes light over 4 years to travel from Proxima Centauri to Earth. And that is just way too far for conventional space craft that use rockets. However, there is a proposal to build tiny spaceships that could get to a speed of like 20% of the speed of light and make the journey in 20 to 30 years. These spaceships don't use rockets. Instead, for propulsion, they use the fact that light has wave-particle duality. So light is made up of particles called photons. Those photons carry momentum p that depends on the wavelength. So if you hit something with a photon, just like hitting something with a baseball, in the collision, you can transfer momentum to the target. So you can set up a light sail, and by hitting the sail with lots of photons, it can give the spaceship propulsion. This has actually been done. This is an artist's rendition of the Japanese spacecraft Icarus that used a light sail and was propelled by photons from the sun. Breakthrough Starshot proposal, a light sail 4 meters by 4 meters, would be hit by photons coming from a multi-gigawatt laser array on Earth that would accelerate to these high speeds and let it travel to the Proxima Centauri system in just a few tens of years, then make a very rapid flyby of the system and let us make images and scientific measurements of Proxima Centauri b. All of these topics are discussed in our Intro First Physics and Astronomy courses, from Newton's laws to orbital mechanics to the photon momentum relationship. These are things that you would learn in just first year of study of physics at the University of Manitoba. If you're the kind of person that questions like these, then I encourage you to consider studying physical and sciences at the University of Manitoba. And these photographs show some of our facilities and students using them.
Okay. I can't hear you.
Thank you very much for your attention. Pass on to Horace now.
Okay, thank you. And just to remind you, if you'd like to ask questions about what you've just heard, just type in the discussion. And I think, Ruth, you can see those, right?
I'm monitoring the discussion and Horace is going to talk.
Very good. Thank you. So, hey, everybody. So I'm Horace Luong from the Department of Chemistry, and I'm the Associate Head of Undergrad Studies as well. So I'll be talking to you about this area called quantum computers. So many of us, when we think of chemistry, we think of students or people working in labs, dealing with chemicals and glassware. That's one part of chemistry. But what I'll introduce today is an area that's right on the frontier of chemistry, and it's very, very useful to us, and how it relates to this quantum computing. And quantum computers is an area that bisects physics, computer science, engineering. So it's a very new area, and there's a lot of potential in that area. So when we think of computers, our classical computer is uses these things called bits to store information, and so bits comes from the word binary digit, so it's stored as either zeros and ones. So when these bits come together, you get things called bytes, and then when many bytes come together, you get megabytes and gigabytes and terabytes. So that's how information is stored in a classical computer. And so what's different in these quantum computers is that the information is stored as things called quantum bits. So it no longer is stored as zeros and ones. In fact, the way that information is stored is using these little subatomic particles, these photons or electrons. And Dr. Ruth just mentioned, using photons for the light sail apparatus. And so many of these subatomic particles have that wave-particle duality, as Dr. Ruth mentioned. So that is, they can exist as particles, they can exist as waves. And quantum computers uses that to its advantage. And so I'm not going to go into the full details of that, but if you want to hear a bit about quantum computing from our Prime Minister, feel free to YouTube his name with quantum computing, and somebody put him on the spot to ask him to explain quantum computing. He did a fairly good job several years ago. So when we're looking at this area of quantum computing, it's a brand new area. And so in terms of what work can be done, you have the software side, developing software to run these quantum computers and how to use the computers. But from the chemistry side, we can look at it as what kind of hardware can we help create? And so this image right here on your right is what looks like the chandelier, is IBM's System 1 model of it, at least. So at one point in time, there were a couple of these, and in 2016, a couple of these hanging around and around the world. And now there's probably close to 20 or 30 of these models. So when we look at chemistry, we can look at how do you create these qubits? What kind of chemistry is involved with creating that little thing to store information? Another way that chemistry can help out is how do you communicate information to the processor? So what kind of materials are used to communicate within the computer? One of the things I haven't mentioned is that when a lot of these quantum computers are operating under really cold temperatures. So as an example, this IBM computer, System 1, is operating at 4 degrees Kelvin. So 0 Kelvin is effectively the coldest place in the universe. And so this is just 4 degrees Kelvin higher. So to cool that down, you'd have to use liquid helium, followed by working in a vacuum to make sure there's no thermal energy at all. So part of the chemistry is, someone could develop materials to help cool that processor down. So that's looking at the quantum computer as a whole, like how can chemistry help out? So when it comes to quantum computing, why is it so important? Why is it such an interesting area? When it comes to processing, quantum computers can operate faster than our classical computers. One of the things to realize is that both classical computers and quantum computers can solve the same things. It's just that with quantum computers, it will eventually be possible to solve things faster. And it all relates to that fact that these qubits can act as particles and as waves. So it will help with that process. Could one day these quantum computers take over our home computers and our cell phones? Not likely anytime soon. Part of the reason is because when you look at these quantum computers, they operate in a very sensitive environment. We have to be careful of things like vibrations, light getting into the system. It would disrupt the computing. And so it's not likely that quantum computers will take over our classical computers anytime soon. So quantum computers are being used right now in various fields. So chemistry, we're starting to use it. And I'll talk about that in a moment. People in finance are also using quantum computers. So it's a very broad area where it affects. So a couple of years ago, Google AI, or Google has been developing quantum computers as well. And this Sycamore computer has 54 qubits, and they matched it against a classical computer, the Summit. And they gave both these computers something to calculate, and then compared the time it took for the calculations to be performed. So Google right away, said, okay, our computer, our Sycamore, has beat this classical computer, and it took only 3.5 minutes, whereas the classical computer would take 10,000 years to do this calculation. And so therefore they declared this quantum supremacy. Okay, so that was just a couple of years ago. There was a little controversial when it came out because it was a very specific set of calculations. And so other companies are more or less trying to match that of classical computers. So one of the things that you may not know is that Canada has invested a lot into this whole computational or quantum technology, quantum computing area. And so in 2005, our country started investing into this area. And it's probably one of the top countries in the world in terms of putting money into quantum computing and quantum technology. And so they predict that, by 2040, there will be over 200,000 people working in this particular field, and there will be, over $140 billion in this particular area. So it's a very exciting area, very new area for us. So when you look at what's in the market today, so IBM, I showed you that System 1 chandelier-like quantum computer. That's one of the bigger company in terms of developing quantum computers. Google, as I said, the Sycamore example, is also in this area. This company called D-Wave is actually a Canadian company. And so I was having lunch today, and then all of a sudden my Financial Post email popped in, and it said, D-Wave has demonstrated performance advantage for a particular calculation using the quantum computer. So they are developing quantum computers. They're working with Google to make commercial quantum computers. So there's other companies as well working in this field since it is so interesting and could potentially be very, very useful. So yeah, there's all kinds of news popping out these days on quantum computing. So many of us who do study sciences, what I encourage people to do, especially students, is whatever you study, try and keep in mind, okay, how do I contribute back to society? And so when we look at the 21st century, there's many issues that we should think about. How do we contribute to resolving some of these issues? So the obvious examples would be things like energy. So can we get away from fossil fuels and go towards other energy types, dealing with climate change, sustainability. So how do we, what kind of materials do we use to ensure that we're working sustainably and living sustainably? There's the health issues as well. Water security, so in terms of having fresh water available. And then there's all kinds of plastics and garbage in the ocean. How do we deal with that? So these are all various types of material issues in the 21st century. And so where quantum computing can come into each of these areas, we can think about it as, okay, how can the computer be used to help us solve those material issues? So can we use this quantum computer to help us design drugs that can tackle viruses or diseases and bacteria? When you look at the purifying water, there's a filter that you have to use. Can we use the computer to design that particular filter? When we look at various reactions in climate change, in the atmosphere, for instance, can we use the computer to calculate that, those particular reactions? So this example here on the right is Roche, which is a pharmaceutical company. They are using quantum computers to design drugs for dealing with Alzheimer's disease. And so, you know, these quantum computers, because they are so much faster than regular classical computers, could be used to solve many of these issues eventually. So when I look in our chemistry department, we've got many researchers, about 23, 24 researchers. Some of them are actually using computational chemistry to solve their chemistry, to help solve their chemistry. So this professor here is Rebecca Davis, and she's working with various professors in the Department of Microbiology, Medical Genetics, to develop, using computers, computational chemistry, drugs, prospective drug molecules to tackle cystic fibrosis. So once they figure out with the computer what will fit into this particular bacteria, they can then try and make that molecule in the lab. So another person that I can highlight here is Dr. Jörg Stedefeld. And so he has partnered with an artificial intelligence company, and they're using this computational chemistry to figure out what will interact with the COVID virus in terms of the protein. And then, so hopefully by gaining the understanding of that protein, they can then finally work on, okay, what kind of medicines or what kind of drug molecules will interact with the COVID virus. And so these are very exciting examples of how computational chemistry can be used in a lab. So, you know, for those interested, if you want to learn a bit more about the chemistry or the computational side of chemistry, we have courses in computational chemistry. It's a 3,000 level course. There's, of course, courses in quantum mechanics. So you can take them through physics or chemistry. And then for those who actually want to get a hand in research in these areas, we do have research project courses that are the 4,000 level. So students can take advantage of that as well to get a chance to actually work in the lab and use computational chemistry. So I realize my time has run short. Okay, there's about 3 minutes before this ends, so I'll stop there. And if you have questions, feel free to put them into the discussion box there.
Okay. Well, thank you, Horace, and thank you, Ruth. Again, as for questions for either person, please just type them, and I'll read one of the ones that just arrived, if you'd like. Oh, no, maybe you've got it. I've just been covered by all sorts of pop-ups. Oh, there we go. Which processes are quantum computers better at solving than classical computers?
And the big numbers, yeah, exactly. So, you know, one of the things to keep in mind is that when you look at these quantum computers, they would be used for processing very difficult, a lot of variable things. Like, you know, when we look at in chemistry, you're looking at environments that, you know, there's all kinds of solvent molecules around. There's all kinds of, let's say, proteins. How does that deal with this particular system? So typically you wouldn't use it to solve a simple case.
There's two more questions from Josh. It's out of curiosity, are those partnerships that you mentioned helped by the university, or is there a process that the students use to connect with those potential partners?
That's a good question. Well, I think that usually these partnerships are sort of initiated by the researcher. So they would contact in this case, it was Atomwise for the AI case with the COVID, and then with Rebecca Davis's group, I think that she formed a partnership with the various researchers, and then they applied for funding through the Cystic Fibrosis Foundation. So,
yeah. Okay. There's another question from Luca. Do these courses have access to maybe run programs on quantum computers? Was that not so common?
Yeah, I think many of these the chemistry course at least, they do use a particular program, but it's not on quantum just yet. And actually, for those interested, IBM does allow people to apply and go into and use the System 1 or one of those computers to do their calculations. So it's great that they have that available.
Okay. There's another question coming, I can see. Typing. Oh my, all these pop-ups. Any more questions from anyone?
My goodness, look at all these pop-ups here. Or maybe people want to move into the next, so they're not late for the next.
That could
session.
be. Well, we can stay here a little bit if you've got time.
Mm-hmm.
We've got 22 people or so. Just.
It was I took a quick read of that article that came out today for D-Wave, and they purposely wrote that they were using a practical system, because I think that was the critique on the Google system, that okay, this is not a practical example, so it doesn't demonstrate that supremacy or quantum advantage. But in this case, it's okay. Whatever it showed it 3 million times faster using this quantum computer.
Oh, there's a new comment. Oh, thank you. Yes. So thank you from Josh.
Oh, Josh.
Questions.
Take care.
I had a colleague I work on areas with small magnetic nanoparticles interacting, and we put them in you can put them in funny kind of conflicting geometries. But anyway, a colleague took the idea to D-Wave, in fact, because you can do other things with D-Wave. It's sort of highly programmable, right? And so they actually simulated that same sort of conflicting system on D-Wave
Nice.
using didn't use real little nanomagnets at all. They just adjusted the phase between their little qubits in such a way as it mimics it. So
it's such an interesting area. This, as an organic chemist, we don't really talk about or hear about this particular area very much. So when I started reading about it, I'm like, what is this qubit? Like, how do you make a qubit? and some people were saying you put a particular atom into a like a silicon cage, and such a interesting field.
2 more questions. Let's see. I think first one's from Declan. Would it make sense to create an online way to use a quantum computer, like anyone could send in a set of calculations and the quantum computer would send back information online?
I think that is already done, isn't it? Yeah.
Yeah, because quantum computers need such a delicate environment, you'd have to remote access it.
Yeah. In fact, for those interested, like IBM just released this video, I think last week, talking about their quantum computers. And it was an hour-long video, lots and lots of information in these videos. And so it's a great way to get introduced to it.
But the question about artificial intelligence, I don't think we've defined what artificial intelligence looks like yet very well.
Okay, what is it? Can I say here? Okay. Some of the things are artificial, almost inevitable. Yeah. Well, yeah. That's a great question. So it's continually learning.
That's another question. How much does a quantum computer cost?
Oh, that's a great question. Like those D-Wave computers, I think are in the millions. And then whereas actually there's a company right now that's producing this quantum computer that's only like 2 qubits or 3 qubits that comes in about $5,000 at least. That's what they're expecting to sell it at. And it's meant for education, right?
Mhm.
For students, but that's only 2 qubits compared to these. These system ones are what, 64 qubits, 70 qubits. And so eventually, I think they're aiming to get up to 1,000 qubits by 2023. So hopefully by then, some of the students have just graduated, and maybe they'll be teaching us, quantum computing things at that point. Yeah.
Mm. Okay. Oh, there's a new one. I kind of want to buy a smaller quantum computer now. Yes.
Yeah, don't we all? Right? Yeah. But I have to wonder, for many of the things that we do, like emails and word processing, we probably don't need it. But for those who do, work in the computational chemistry or physics area, yeah, sure, be very, very useful. I don't know if it has any effects on gaming.
Yeah, gaming, Bitcoin.
Yeah, Bitcoin mining. That's right. Yeah. Yeah, that's a whole interesting area. That's okay. Can we use these things to crack encryption in the financial areas, right? Yeah.
Well, you can turn it the other way around. I think you can also use qubit technology to make something which cannot be
Yeah,
broken.
exactly.
There's a comment about Shor's algorithm.
Oh, wow. That's beyond my my knowledge. But that is.
Let's see. We've got. Do you want to stay on a little bit longer, or?
I actually have another event to go to in a few minutes, so I'm going to have to leave.
Okay.
All right.
Sure.
Well, I can stop recording. And I want to thank everyone. I think there's still a few people left in. Want to thank all of you for attending, and especially thank you, Horace and Ruth, for your presentations.
Well, thanks everyone for attending. I
Great.
was worried.
Thanks.
Bye-bye, everyone.
Take care, everybody.
I will stop recording.
Okay.
And stop the broadcast.
Okay.
Great.
Then...
Okay. What do we need to do?